planet. I don't know of any such law today.
So let me ask you both this.
But there's some thinking that, and this is wishful thinking, not because someone has researched this, that you go to a different planet, you can take a geologist there, they'll be comfortable there because they'll know what a rock, there's an igneous rock.
Because they see their crap everywhere.
Yeah, that's right. Yeah. So the rocks and the minerals, there might be some more exotic ones.
Exactly.
But they have a sense of what elements do when they're heated for a certain amount of time under pressure.
Right.
And that repeats depending on the planet. So there are general rules of geology that apply to all planets.
To all planets.
So let's go to biology.
Okay.
Could the DNA molecule be a natural consequence of complex chemistry operating on planetary surfaces? Could it be as natural on a planet as rocks are to the geologist?
And that's what I was about to ask, and both of you can chime in on this. How cheap is life? So forget if it's inevitable. How cheap is life?
I don't know what that means.
Well, in the sense that it formed relatively quickly on planet Earth. So it didn't take an enormous amount of time.
If it took billions of years, you can say, whoa, that was some hard stuff. Yeah. It formed in fact, we used to, how long do you think it took?
Half a billion, I'd say.
Okay, that's what we used to say. Okay.
What would you say now?
Okay. We used to say that because you'd start the clock at when Earth formed, right? 4.5 billion years.
billion years.
Yeah. And then the early signs of life were like 3.8, 3.9. So you say 600 million years, we used to say. And then we said, no, that's unfair. That's unfair. When Earth formed, there was periods of heavy bombardment where the surface of the Earth could not have sustained complex chemistry.
Of course.
Because the energy is too high, it breaks apart all. Let the Earth cool, for goodness sake.
Yeah.
So the cooling, it let it cool at about 4 billion years. That's half a billion years. At 4 billion years, now you start the clock. And you have life 200 million years later.
Wow. That's really quick.
Right.
Yeah.
Right.
In the grand scheme.
In the grand scheme.
Yeah, so that's what I'm saying. So life is pretty cheap then.
Yeah, it's 5% of the total time Earth has been around. So
again, however, I think that's likely the way to talk about it, but there are so many detailed physical chemical processes that maybe they just so happen to come together in this one planet of the trillion that are out there. Right. So when we understand it better, that cheapness, we may explain it by a coincidence of a whole lot of factors that just happen to align on our planet. I don't think that's how it's going to turn out, but it's a possibility.
It's a possibility, yeah.
Well, except that, there are amino acids on meteorites.
Yeah, we found them already.
Right.
Yeah.
An interesting question, though, is the way that proteins are coded by amino acids is uniform across all life. It's the same code. 3 base pairs on the genetic code give rise to a particular amino acid. That is the code that works for you, me, and all life. On another planet, if there is other form of life, the deep question will be, is it the same code?
Right.
Or is it different? So
it doesn't need DNA at all.
Right.
And so if it's different, that would be wonderful. That would suggest that life in a whole variety of different forms can exist throughout the universe.
Fully explored all the ways of being alive.
Exactly.
Yeah.
Wow. All right. Well, great question. Way to go, Cody. All right. This is Aaron Bailey who says, "Hey, Star Talk. I am Aaron from Florida, and we're sorry."
Florida's trying. They're trying. All right.
Yeah, so Aaron says, longtime viewer, first-time subscriber. Thank you, Aaron. We appreciate that. According to Einstein's equations, is time travel still possible if you are traveling to a black hole? And why can't we use gravitational detectors to measure the properties of dark matter?
So in the first question, Einstein's special and general relativity both embrace a certain kind of time travel. And the black hole provides the mechanism for one kind. If you go hang out near a black hole, time for you elapses more slowly compared to someone who's far away.
Famously portrayed in
Interstellar. And so if you go to the edge of a black hole and you hang out and then you come back, everyone that you meet is going to be much older. Their clock was going much faster than your clock. And that is, some people say, well, that's not time travel. That is time travel.
It certainly
You've traveled into their future, which would have been your future if you stayed there. Exactly.
And you know who they left up in the ship?
The black dude. He came back like, oh, goddamn.
23 years. 6 hours.
I seriously, now, I'm on Social Security. I don't get it. You go down there, you tell me you come right back. You're worse than my kids. You're worse than my kids. You're worse than my kids. I don't get it, Matthew McConaughey. All right.
What was the second half to that question?
What was the other half?
And so the second half, he says, why can't we use gravitational detectors to measure the properties of dark matter?
Well, we do. The way we know dark matter exists is by the gravitational influence that it has on its environment. What we're unable to do is identify what the dark matter is made of.
Right.
And so we have these detectors all over the planet trying to capture little particles of dark matter, if that's the right explanation.
Right.
We haven't been able to find any yet.
What? You know what we're doing now?
What?
Okay, you know they're pulsars.
Yes.
They're rapidly rotating neutron stars. They
In a
give
very
radio
precise way.
Extremely precise.
Right.
And they're across the galaxy. There are not all that many of them,
right.
but there's enough to map out the galaxy. So if you precisely know and measure the pulses of these pulsars,
Okay.
you can track a gravitational wave moving across the galaxy.
Yeah, so
From
you're
one
kind of
pulsar to
using
the
them
other.
like buoys in the
Buoys.
ocean.
Oh, yeah, good analogy there. Beautiful idea, and you don't even need LIGO for that.
Yeah.
Right.
You just need high-sensitive, high-precision time.
Yeah, for gravitational waves of a certain wavelength, this is a beautiful way of detecting their influence.
Super cool, man.
Yeah.
All right. Let's move on to Alex Frias, who says, hey, Dr. Tyson, Lord Nice, Alex here from Mexico. Oh, I should say Alex.
No, Alejandro.
Alexandro from Mexico.
What? Isn't that racist that you assume?
I can be racist. I'm black. I don't know if you realize. Okay? The world invented racism for me. Okay, here we go.
From
He
Mexico.
says,
Did I tell you? It was. I was giving a public talk, and I thought I'd say something funny.
Right.
I was talking about the dinosaurs, and they went extinct by an asteroid that hit the Yucatan Peninsula of Mexico. And I said, but that's not what the dinosaurs called it. Okay.
Okay.
I thought it'd be
That's
funny.
funny.
I thought it'd be funny.
Right.
I thought it'd be funny. And then someone in the front row said, they called it Mexico.
that's funny too.
Spanish
full of dinosaurs. Yeah.
Okay. All right, go.
Right. And then you had Trumposaurus, who was just like, keep them out. Anyway, I've always been intrigued and confused by the idea of supersymmetry.
Ooh, nice.
If the standard model of particle physics is one of the most successful theories we have, what is telling us that it needs doubling up? What would supersymmetry fix in our understanding of the universe, and what problems might it create? Thank you both, and greetings from your neighbors in the beautiful Upper West Side.
Oh, nice.
Oh, look
nice,
at that.
nice.
Way to go, Alex,
Upper
from
West
right
Side
up the street.
of Manhattan.
Yeah, right.
So let me sharpen that even further.
Sure.
So the standard model is quite an organizational map of our particles and our forces and the like. In its current state, now that we've got the Higgs, is it missing anything? Is it a closed box right now? And if we do anything to it, does it simply make it more powerful, or do we know we need things to explain other things that we don't yet understand?
Good. So the main motivation for supersymmetry is to address exactly the way you frame the question, which is when we study this Higgs particle, this newest addition that we found on July 4th, 2012, at least that's where the announcement was. When you look at the mathematics, it says that the mass of the Higgs particle should be much, much bigger than the mass that we find.
What?
Really?
And when we try to keep the mass at the value measured, we have to stand on our mathematical heads to do so. We have to tune and tune and tune. If supersymmetry were true, the terms that would push the Higgs mass up, they cancel out from those pairings. That's why we need the pairings. That's why we need the doubling. And if you can cancel out the new contributions, you can rest easy. The Higgs mass will stay at a small value.
Look at that.
So how many more particles come along?
It doubles it. It really does. For every known particle, there is a partner.
There's
Electrons
a
have
supersymmetric partner.
Yeah,
Do
supersymmetric
we have words
electron.
for all these
Yes,
particles?
so the electron has the selectron, quarks, squarks, neutrinos, sneutrinos.
No.
Yes.
No.
Yes. I don't name them.
Neutrino.
Yeah.
No.
Yeah.
You know why? Because somebody, when they found it, they were like, neutrino, sneutrino. Okay.
And so the big hope, if you would have spoken to me when I was a graduate student in the 1980s. The big hope and the reason we believed that string theory might be 5 years away was we expected supersymmetry, which is the super in superstring theory. We thought it would be found. Those particles would be found at the Large Hadron Collider. And they were not found.
Wow.
And so this
And
did
they
not...
will never be found.
Well, that's probably true because the collider has a limited energy reach. Nothing in our theories tells us how massive the partner particles would be. If they're sufficiently massive, they'll be beyond the reach of the Large Hadron Collider. So there's a natural explanation for why we didn't find the particles, but we were certain that we would.
He wants another collider.
Yeah, there you go.
Yeah.
You're going to need one.
That's what it sounds like.
Look at that.
All right.
Well, that is fascinating, though. Okay. And does the Higgs have do we have a name for the other particle?
Higgsino.
Higgsino.
Yeah.
I prefer squigs. As long as you're going
If you're
there.
going to go with squarks, you might as well
Give me
go with
some
squigs.
And how about the photon? What's the symbol?
Photino.
Really?
Really?
Okay.
And the W and Z bosons, those are harder. Xenos or Wenos.
Wenos. Yeah,
Wenos.
No,
getting
they
there,
get
yeah.
a little bit, yeah.
That's
but-
getting a little funky.
Okay, and how about the graviton?
Well, you see, the supersymmetry that we're talking about doesn't have gravity in it when you're just talking about the standard model.
Oh, Santa Monica doesn't have gravity.
yeah,
It's not
yeah.
there.
But if you include gravity,
Right.
then there is a version. It's called supergravity, and it comes out of string theory as well, and it's the gravitino.
Right.
Okay, all right.
It's from the graviton.
Yeah.
Right, okay.
Okay. All right. All right. Well, way to go there, Alex.
So we're still looking for him.
Yeah.
You're still looking for them. There's no evidence
Okay.
for them. Yeah.
Is this just a matter of a lack of detectors? Could you build enough detectors where we could get all this, capture all this stuff?
Not so much detectors, it's a matter of the energy. So how big the
How big the
collider is.
right,
And
right.
that's, colliders are expensive, and the
Yeah.
bigger they are, the more money they cost.
And we had a big one going in our, in our side of the pond. The superconducting supercollider in Texas,
Right.
funded in the 1980s under Reagan.
Right.
And we dug the hole, got all ready. Waxahachie, Texas. It would be 3 times as powerful, I think.
Yeah,
as,
about 50 TeV, and we have 14 TeV.
Yeah. So 3 times
Yeah.
the power of the one that was built in Switzerland. And then early 90s, they zeroed the budget. And they said, there was cost overruns and this sort of thing. But
Oh, some kind of defense thing. We no longer were fighting for our
peace
lives.
broke out
Yeah.
in Europe.
The fall of those.
Yes.
Yes.
Peace breaks out, and all of a sudden, it's like, we don't need
We don't need
physicists.
this, we need this.
What do we need physicists
Right.
for? And their little toys. You never heard of cost overruns in any other particle accelerator for the whole 20th century.
Right. Interesting.
Yeah.
This is Blake who says, "Hey, it's Blake. Greetings from warm, sunny Columbia, South Carolina."
Oh,
way
okay.
to rub it in there, Blake. He says there are quite a few theoretical particles that have been discussed on this show, the graviton, the tachyon strings, etc., but we don't seem close to actually finding any of them. Are there any experiments proposed that might help us capture and learn about these elusive particles if they exist? And slightly more an engineering question, if we did find them, how might we use them for the benefit of humanity?
Yeah.
Do they have a use if we find them? I mean,
Well, if dark matter is actually found and it is a particle, look, it'll deepen our confidence, our understanding. Can I imagine applying dark matter particles to build something? The whole point is they're incredibly elusive. They only interact
I was gonna say,
gravitationally.
how do we even capture them
Yeah.
if they don't interact
even-
with anything?
They don't even
Well, they do interact.
with themselves.
They interact with
much.
themselves.
Yes, but anything that has energy interacts gravitationally. And these
good
dark
point.
matter particles, through indirect quantum processes, do interact with ordinary matter. And
They would
that's
have
how
to be
these
because
detectors
the
are set
universe
up.
is accelerating. Or is that the energy?
Yeah, well, yes, you could. Well, that's the dark energy.
That's the energy.
Yeah, but
Okay.
it's the same basic idea.
Okay.
And so, yes, you can detect these things, but that's different from gathering them together and engineering with them. So I don't see any direct benefit
There's
that
no
comes
bricks
out.
and mortar.
Right.
But again, it's the same argument we made before. The deeper your understanding,
Understand.
that's step one.
Who
and
knows
then
where that's
someone
going to
figures
take you.
out where that goes.
That's
Somebody
going
else
to take you
figures it out.
someplace
Yeah.
else,
Yeah.
right? Okay, gotcha. All right, this is Luke Sr. who says, best regards from Joliet. He says, Dr. Luca Laporta, PhD, translation scholar and sinologist. He says, could it be the entanglement phenomenon is simply a matter of absence of the time dimension at the scale of the particles, and that we see two particles interacting instantaneously at a distance in some, his word, magical way. In their own 3 dimensions only universe, they're just unaware that a change of state has occurred, that for them, there's no before entanglement / after entanglement. Thank you very much. It's a very well thought out question. Does it make sense?
It does, and I think we can interpret it more or less along this wormhole idea that we were describing before. The wormhole notion, again, this is still very much at the forefront. We're still working out the details. But if it is the case that 2 distant particles are connected by a wormhole, if they're entangled quantum mechanically, then it would be as if they're right next to each other.
Right. Yeah. To them, they don't know the difference.
To them, they don't know that they're far
exactly.
apart. And so that's a variation on the same thing. I don't think you can say they live in a world without time, because the conundrum is, to us beings that do have time, you do something here and it instantaneously, according to us, affects something over there. And that would still be a puzzle no matter what.
No matter what.
And one explanation would be, well, they're actually closer together than you think by looking at them, because they have this secret shortcut connection, which could be the wormhole.
So I think for so many years, people were imagining wormholes as some kind of ride in a water park.
Exactly.
Even in the movie Contact.
Right.
Jodie Foster is going through. And so, but no, you just step through.
No, you step through.
I think it depends on the nature of the wormhole, but yeah, there can be versions where it's effectively stepping from one place to another.
Star Trek did it right, though. They had a portal where it looked like a doorway threshold.
City on the Edge of Forever.
City on the Edge of Forever.
Yeah.
And that's a wormhole. You step through it and you're already there.
Mm-hmm.
There's no ride. There's no, you just step through it and you're already there.
And that's another one where they were going to save someone's life. And they decided not to.
And they realized
what they're going to change the future.
Yes.
Yeah.
In fact, I was talking with Bill, and he said that was his favorite episode.
Oh, really? Yeah, it's my favorite watching as a viewer.
Yeah, just because it dealt with time travel in a very
emotional way.
Emotional and unorthodox way.
Yeah.
And causality is actually addressed. All right, Zachary E. says, hello, Dr. Tyson, Lord Nice, Dr. Greene. Is it possible that through the many worlds interpretation, quantum immortality can become macroscopic? If every single possible state of every single particle in existence is equally real, I feel like the superposition of a single particle in quantum immortality theory can be expanded to incorporate the superposition of every single particle in existence.
Yeah. And look, another way of saying it is, we said before that the many worlds allows a world in which anything compatible with physics is realized. Us living to 100, 200, 500, 1,000, I don't know that there's a law of physics that prevents that can happen.
Now, there is a law of Jesus, I'm bored, that will allow that.
The boredom.
The boredom. Can you imagine living 1,000 years? Kill me. Just thinking about it, I want to die.
Wait. Here's something that we did not raise, which was, if there's another identical me, is it me?
That's the deep question.
Wow,
that is the question.
That's a consciousness question.
And I think the answer to that is yes. Because
I think the answer is no.
Why?
Because we've already kind of done that experiment. They're called twins.
No, I'm saying that person has literally your memories, literally your sense of self, until measurement happens that causes you to be different
from that.
Yeah. So it's truly you.
That's wild.
I mean, if I spoke to that version of you, you would adamantly claim, yes, I'm the same guy.
Right, that's me.
It's me.
It's me, damn it. That's funny.
Yeah.
I don't know what to say.
I've never heard you say that
before. So that means we are living forever. The reincarnation folk are all over this.
That's right. Right.
Why?
Or at least extraordinarily long. Maybe there is some physical law about maybe the proton decays in 10 to the 38 years. That kind of
38.
Yeah,
well,
or 10 to the whatever.
More than 10 to the 32.
Yeah.
32.
Wow. All right. This is Marcus Ruzon. And Marcus Ruzon says, Hello, Neil and Brian. Love the show. I've been wondering something about time and light. If nothing can travel faster than light, and the speed of light is a universal constant, could it be that time itself is actually an emergent property of light? Is it possible that what we perceive as time is actually just a consequence of us traveling through space-time at a finite speed below the speed of light? Is that not confirmed by the fact that from the point of view of a photon, there is no time, thanks, and keep looking up from Singapore?
Yeah.
Nice.
Okay.
And in some poetic sense, I agree with what the questioner asks.
Yeah.
They're saying that if a photon had consciousness,
Right.
from its perspective,
It would not know.
It would not know that time is
There's no
elapsing.
such thing as time.
Now, I think it's really important to recognize that you're extrapolating Einstein's result to a particle for whom the equations don't literally apply in the way that we're using them.
Correct.
So if you apply Einstein's ideas to any massive body, you find that they can't travel
right.
at the speed of light. And therefore,
Right.
they will always have this conception of time.
Exactly.
But if you want to push it to the absolute limit, which I call poetry, not quite mathematics, then yes.
Right. Because the key is the photon has no mass.
Yes.
That's the key.
Yes.
That's it.
Yep.
So once you have mass, you can't be a photon, and you'll never experience what that photon experiences.
Precisely.
All right. Okay. Well, there you go, Marcus. But thanks for the,
I had nothing to add to that.
All right. This is Patrick Dietz. And Patrick says, hello, Dr. Tyson, Dr. Greene, Lord Nice, Pat Dietz from Ravenna, Michigan. Could the reason we cannot see dark matter also account for the expansion of the universe due to dark matter moves faster than light? Let me read that again. Could the reason we cannot see dark matter also account for the expansion of the universe due to dark matter moving faster than light? Okay.
That's a tough one to parse
Isn't
for
that
me.
really rough? But
Yeah.
I see what he's saying. How can you see the thing that's faster than the thing that allows you to see the thing?
Right. I get this sort of collection of words, but the problem is...
Okay, by the way, people,
It's a satchel of
listen,
words.
This is why I love scientists, because they know how to call you a dumbass without ever saying those words. See,
The important point is that for a particle to be a particle of dark matter, it has to have mass.
Right.
Once it has mass, it can't travel faster than the
than
speed
light.
of light. So
Right.
the ideas don't meld together in a consistent way.
there you go. All right. I like the question, just for the fun of it. All right. Thank you, Patrick. This is Mr. Zoot. And Mr. Zoot says, Dear Star Talkers, Jeffrey here, pronounced Jeffrey, Chuck. Screw you, Mr. Zoot. He says, I understand electron orbitals are really probability clouds, but still exist in discrete energy levels around the nucleus. What then happens during ionization? Do they stay as a probability cloud, just untethered from their anchor, so to speak? Do they still have discrete energy levels? Hey, what gives? And thanks.
So if that,
That
it's a great
yeah,
question.
Somebody's thinking.
And so it certainly does stay as a probability cloud or probability wave if an electron
If
is
it's an ion.
ionized, say, from hydrogen. But if that electron is living in a universe that is not a box, that's infinitely big, then we don't believe its energy levels will be quantized.
You think it'll be continuous?
Yes. So if you have a particle
Oh
in
my
a box,
God.
if you have a
Uh-oh.
particle in a box, then the energy levels are quantized, but they are dependent upon the size of the box.
Because
Okay.
you're solving the wave equation.
You're saving the wave
Or
equation in a
what do you call
box.
it? You're expanding what's it called?
The harmonics.
The harmonics
Yes.
of the wave.
And the harmonics have
They have
to
to fit
die.
inside the box.
They have to fit inside the box. But if there's no box, then they could have any wavelength at all,
What you're
any
saying is
energy
that
at
the
all.
energy of a free electron is not quantized.
Correct.
I did not know that.
I've never
Now
heard that
you
before
explained
either.
it. It's obvious that it could only be that way.
That makes that's wild.
Wow.
That's absolutely wild. Very cool, man. Wow, great question,
And
Jeffrey.
just to highlight, because he said something important here.
Yeah.
So we'll call it a box, but let's look at a tube. Let's look at an organ tube.
Okay.
Okay. So
Like a pipe organ.
Pipe organ.
Right.
And you can ask, what kind of wave can you set up inside that tube? And it can only hold a wave where the complete wave is there.
Right.
You can't hold like a half a wave. Right. So it sets what the wavelength is, so the frequency of the sound, that's the wavelength. You get that from the wavelength in each tube. So different tubes have different frequencies that resonate inside of those tubes.
Right.
And so when I think of atoms, I think of, you got the nucleus with the protons sets up a box. And so you do the math and you get a set of wavelengths, I'll call them that fit inside this box. And it's unique for every atom. And that's what gives you the spectra of each atom.
Oh, nice.
That's so each atom has a unique spectrum.
Right.
Yeah. It's really cool.
That is excellent.
Yeah.
Wow. I learned stuff on this show. It's so great.
So did I. I just never thought about free electrons and their energies.
Yeah. Okay. This is Brian Nadeau, who says, hey, Dr. Tyson, Dr. Greene, Lord Nice, Brian from upstate New York here. Would the discovery and verification of the graviton assist at all in reconciling general relativity and quantum mechanics?
Huge.
Isn't it just assumed that there's a graviton?
And that assumption needs to be verified, hopefully.
And what's the energy of a graviton relative to the waves that we just detected?
Well, the energy, the mass of a graviton, we believe, is zero, because gravity also travels at the speed of light. So it's much like a photon in that particular way. And yes, if we could ever really detect a graviton, do experiments with gravitons, scatter gravitons off of each other, then yes, we would learn an enormous amount about general relativity and quantum mechanics.
Yeah, but will it help you merge them?
Well,
because that's a quantum expression of gravity.
That's right. In fact, the very existence of a graviton would be the first evidence that gravity is quantized.
Right.
Wow.
And so we're assuming that there is a graviton, but verifying it would be a huge step.
Who was the first to presume that?
The idea of the graviton? I don't historically know.
But Einstein was the gravitational wave.
Yeah, well,
so where you have a wave,
he was a reluctant gravitational wave person. He was really uncertain in 1916 and 1918 about whether they were real.
Okay.
Amazing.
Yeah.
So I'm just saying, the quantum assumption is that where you have a wave, you also have a particle.
Yeah.
And like the photon is a wave and a particle.
Yep.
Okay.
Mm-hmm. Wow.
Okay.
That's super cool, man.
That's a good question, though. Who first introduced the very idea of a graviton? I don't know the answer.
It feels kind of natural if you're going to.
I'm going to look that one up.
Quantify.
Yeah.
All right. This is Tash Shaw, and Tosh says, Dear Dr. Tyson, Dr. Greene, Lord Nice, I'm Tosh from Orange, Australia. I'm a longtime listener, so my boyfriend bought me a subscription to Patreon for Christmas.
Oh, nice.
Very nice. What a nice boyfriend.
Very nice gift.
Yeah. Now, that's a smart man. I have read that other dimensions could potentially be detected through gravitational and other anomalies.
Yeah.
I was wondering how we would be able to distinguish these from any effects of dark matter. So, would there be dimensional differentiations?
Yeah. In fact, a proposal that was made a while ago is that at a collider, like the Large Hadron Collider, when you slam protons together, you can calculate and measure how much energy you have before the collision. You can measure how much energy you have after the collision. And if you have less energy after the collision, that energy must have gone somewhere.
That is so cool.
And the possibility is the energy went into the other dimensions. And so this was a missing energy signature of extra dimensions that we were again hoping we would see.
Why
but
would
we've
you
not.
presume that and not as what occurred in the first neutrino experiment?
That's right. So it could be some other particle, mysterious particle carrying away.
Right.
But there's
the first neutrino, they did an experiment and there was
an imbalance.
Yeah, there was an imbalance. There was like, you start with this much energy and they have less.
Right.
And you accounted for all the particles.
Right.
So
you're like,
what's up with
maybe
that?
there's another particle.
But what's up with that? And they said, if there is a particle, it has to be neutral and it has to be very low mass. And the guy who proposed it was Italian. So little neutral one, neutrino.
Oh.
Like Bambino, little
Like
baby.
Bambino, neutrino.
What you got, Jack?
Let's go to Cosmic Moss. Says, hello, everyone. Love the show and every star you've had on it. You guys are great. I love the way you teach. Please keep the education up. Dr. Tyson, Dr. Greene, could theoretically a frequency be matched at 2 points in space by a microparticle uninhibited by resistance, only to be met by its astrophysical counterpart?
Neil, I think you should take this one.
I don't know that I understand the question.
Kind of like matter, antimatter, but the particle is already in existence, and then it's a counterpart that impedes, I guess, the entanglement. It's kind of like...
Okay, read the first sentence again.
All right, he goes, could theoretically a frequency, all right, so that's the, I guess, his version of the string, be matched at 2 points in space by a microparticle. So that's the entanglement.
Maybe.
Uninhibited by a resistance, only to be met by its astrophysical counterpart.
The only counterpart particles are antimatter.
That's it.
Yeah, there's no other.
That's what I'm
thing.
saying.
And there's not much antimatter in the universe.
Right.
In fact, well, other than the centers of stars, we probably make all the antimatter there is in the universe on Earth. Would you say?
I haven't done the calculation, but I can imagine that.
I mean, just think about that, right?
Yeah.
I mean, there's plenty of antimatter made in the center of sun.
Most antimatter in the universe will get annihilated, finding matter.
Immediately in the centers of the sun. So,
Right.
the cool part was in one of the Dan Brown stories, the Catholic Church had a vial of antimatter that they carried.
That's so funny. Dominus is spirit. Oh, he's gone. Physics jokes, people. All right.
So yeah, I'm not quite clear. If it met its the counterpart, it would annihilate, no matter what else is going on.
No matter
there.
what else is going on.
Yeah.
All right,
Okay.
so here we go. Kenny Watts says this. Hey, Dr. Tyson, Dr. Greene. What's up, Lord Nice? Kenny from Dothan, Alabama. Is the reason why we can't reach the absolute 0 degrees in temperature because of the CMB? Is it due to the act of time using energy to move forward, creating heat? And if we were to reach absolute 0 degrees, would space-time move forward in that region?
Yeah.
I have different pieces of this, Brian. So my understanding of absolute zero is that, all particle motion stops, except it doesn't because you have quantum fluctuations, even at absolute zero.
That's the key point right there. Yeah.
Okay.
That's the real barrier.
Okay, but why isn't the cosmic microwave background a barrier?
Well, if you didn't shield yourself from 2.7 degree photons,
Yes.
they would influence. But presumably, if you're able to shield your environment.
Yeah, but the shielding would have to be temporary because the heat transfers.
Yeah, sure. But an experiment takes place over a period of time. So as long as your time scales are set right.
That's how a thermos works.
Yeah,
There's
exactly.
a time with which it is.
So I think it's really the uncertainty principle is the true barrier against truly having particles at a definite location not moving. That would mean position and speed were both nailed down at the same time.
Which is not
and you
happening.
can't do
Right,
that.
you're not going to do that.
Not happening.
Wow.
Yeah.
So the wave function would cease to exist if you were ever to get to the place where you could get the particle to stay exactly frozen, like still and definable in 1 point.
Okay, so what is the temperature of that state of matter?
Well, it depends on the details. I mean, you can calculate the quantum fluctuations of a field, and if you tell me how it interacts and its mass, you can calculate its quantum fluctuations, and indeed, that's how you make predictions about the Casimir effect, where you have two metal plates and there's empty space between them.
Evacuated completely.
And yet those plates can pull together because the fluctuations of the field inside are a little bit less than the fluctuations outside. And that imbalance, you can actually calculate it and you can determine how the plates come together.
That is so freaky, man.
It's all freaky.
That is so freaky. I love it.
It's all freaky.
Oh my goodness. And then they attract.
Yeah.
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 Brian, you freaky dude. So we should do this every week. What do you think? No, Brian, you have a life. Thank you, Brian.
My pleasure.